And hello, everyone, and thank you for joining us for today's e-showcase, Sustainable Phosphorus Removal. I want to take a moment to thank our sponsor, Chimera. Thank you so very much for sponsoring today's event. I do have the pleasure of introducing today's presenters, Chris Hill, Marketing Manager with Chimera Water Solutions, Richard Waterous, Senior Account Manager, Chimera Water Solutions, and Ricardo Colon, Senior Application Specialist, Chimera Water Solutions. And without further ado, I will hand the presentation to today's presenters.
Thank you so much for the introduction. It's a pleasure being here today. This is Chris Hill, and I'm excited to tell you more about phosphorus and to hear your questions at the end of the presentation. Today, I'm going to give a general overview of the impact of excess phosphorus when it's introduced to natural waters. I will go also into discussing how this serves as a backdrop for the development of regulations related to phosphorus that we see today. My colleagues will then review methods to prevent phosphorus from entering natural waters to comply with laws and regulations. So first, what is phosphorus? Phosphorus is an element that occurs naturally and is found in large quantities in inorganic deposits. Phosphorus is one of the vital building blocks for life. It is essential, for example, for animal feed and food production, and it is mined and combined with nitrogen, potassium, and other nutrients to fertilize agricultural crops, gardens, and lawns. Phosphorus can be found in the free state as PO4 3-, dissolved in water, often called orthophosphate, or in polymeric di, tri, and other condensed phosphate forms. It can also be organically bound as it is found in biological systems. Some of the biologically bound forms of phosphorus are listed here. Because biological systems are dependent on adequate phosphorus, when an excess of phosphorus is released into the environment from wastewater and agricultural sources, an overabundance of plant growth occurs, leading to problems in the ecosystem. Even if you don't work in the water treatment industry, you've likely heard about the environmental impact of phosphorus. So let's review exactly what is the problem with elevated phosphorus in our natural waters. The diagram to the right was taken from a web page titled NOAA Forecasts Above Average Summer Dead Zone in the Gulf of Mexico. NOAA stands for the National Oceanographic and Atmospheric Administration. The diagram on the right-hand side depicts the Mississippi River watershed, which encompasses over 40% of the continental U.S. and crosses 22 state boundaries. The area is made up of farms, depicted in yellow, cities in red, and natural lands in green. Nitrogen and phosphorus pollution in runoff and discharges from agricultural and urban areas are major contributors to the annual summer hypoxic dead zone in the Gulf of Mexico. And you can see that hypoxic zone depicted just below the coast of Louisiana in the Gulf of Mexico on the diagram. So the process of eutrophication, where excess nutrients cause algae overgrowth, is followed by death and decay of algae by aerobic bacteria, leading to oxygen depletion in water bodies that receive discharges from municipal and industrial wastewater treatment plants. Eutrophication, because of oxygen depletion, causes harm to aquatic life and creates dead zones. Excess phosphorus in wastewater can also result in other environmental and health complications, namely when algae proliferates into biomass. Some of it may be converted into harmful algae blooms that are toxic to humans and animals and create some aesthetic issues such as taste and odor problems. While each organism has its own dissolved oxygen tolerance range, generally dissolved oxygen levels less than 5 milligrams are considered stressful for fish, and levels less than 3 milligrams per liter are too low to support fish. Dissolved oxygen levels below 1 milligram per liter are considered hypoxic and generally devoid of life. No fish, no birds, no sharks, no shrimp or crabs. The ecosystem collapses. There is a lot of US government, state and local government, and non-government contributors to the MARB Hypoxia Task Force. MARB stands for the Mississippi Atchafalaya River Basin area. Shown on the left is a report to Congress from the task force assigned to MARB. And as you'll note on here, the hypoxic zone, which again is depicted below the coast of Louisiana in the diagram on the left, can vary in size, but is often over 8,000 square miles. That's equal to 22,000 square kilometers, or roughly the size of New Jersey. Again, no fish, birds, shrimp, crabs, or sharks. Imagine being a commercial or sport fisherman and having to navigate around this large dead zone. More fuel, more time, labor costs. Also, each summer, there are greater than 40% of the area and 5% of the volume of the Chesapeake Bay becomes a dead zone. So there are big problems to be resolved in reducing nutrient pollution, again, primarily phosphorus and nitrogen. We are focused on phosphorus today. So what is being done about excess phosphorus? Let's take a look at the legal and regulatory framework that is driving limitations on phosphorus control. In our case, this is point sources of phosphorus, namely municipal wastewater treatment plants. First is the Clean Water Act. That's a federal law aimed at maintaining and restoring the chemical, physical, and biological integrity of the nation's waters. The next is EPA regulations. The EPA sets national standards and guidelines for water quality and pollutant discharge. Next is state environmental agencies. The states are authorized to implement the Clean Water Act through their own environmental agencies. States may develop additional regulations that are more stringent than federal standards. Next is National Pollutant Discharge Elimination System permits, NPDES permits. States issue NPDES permits to regulate point source discharges of pollutants, including phosphorus. Permits include specific limits and monitoring requirements. Next is water quality standards. States establish water quality standards for their water bodies based on their intended use. This includes criteria for phosphorus levels. Standards are reviewed and approved by the EPA. Total maximum daily loads. For impaired waters, states develop TMDLs to limit the total amount of phosphorus and other pollutants. A water is impaired if you can't meet the water quality standards required for a desired use. TMDLs are submitted to the EPA for approval. Monitoring enforcement. States monitor water quality and enforce compliance with NPDES permits and water quality standards. Violations can result in penalties and corrective actions. Finally, there is public participation. States provide opportunities for public input and involvement in the development of water quality standards, TMDLs, and permits. There are also options for the public to provide input during the rulemaking process at the EPA. Established based on a water's designated uses, water quality criteria consists of limits on the amount of toxic chemicals, nutrients, bacteria, heavy metals, and other contaminants that are allowed to be present in a wastewater treatment plant's discharge. These limits are specified on a particular plant's NPDES permit. A waterway is impaired if contaminants exceed established water quality standards for a particular designated use. For example, the intended use of the Gulf of Mexico water for fishing is impaired due to nutrient pollution. So the tributaries to and along the Mississippi get a lot of attention regarding prevention of excess phosphorus contamination. Effective phosphorus removal from wastewater is crucial for maintaining ecosystem balance and protecting public health. Under the Clean Water Act, the US EPA has adopted a national nutrient removal strategy to clean the nation's waterways. A key objective of the strategy is total phosphorus reduction. While much discussion has occurred about the need for stricter phosphorus limits in the future, the current reality is that many states have adopted regulations limiting the allowed phosphorus concentration in wastewater effluents. It is common to see statewide regulations limiting those concentrations to 1 milligram per liter or less. Many discharge permits have a 1 milligram per liter limit, but there may also be future ultra-low phosphorus limits as low as 0.5 milligrams per liter, 0.2 milligrams per liter, or less. Some states set statewide limits on phosphorus. Illinois is one. The current limit is 1 milligram per liter, and the future limit is 0.5 milligrams per liter as of January 1st, 2030. Stricter standards may already apply in specific permits. In an NPDES permit, the limit will be expressed as a total maximum daily load, often in pounds per day as the TMDL. To determine the allowed concentration, you would need to know the flow of water in gallons and multiply this by the concentration in pounds per gallon of phosphorus, and thus limit the flow, concentration of phosphorus, or both to stay under the allowed TMDL. My colleagues will now explain methods to control phosphorus.
Phosphorus accelerates eutrophication in bodies of water that receive discharges from wastewater treatment plants. State regulatory agencies require the removal of phosphorus from wastewater to control its harmful effects. Two widely used methods utilized to remove excess phosphorus from wastewater treatment plant effluent are biological treatment and chemical precipitation. Although there are several ways to treat and remove phosphorus from wastewater, the primary and most employed method has been through chemical treatment of wastewater using iron coagulants. Chemical precipitation using iron-based coagulants offers a robust, reliable, and fast-acting solution to phosphorus issues. When iron coagulants are dosed in wastewater, the iron cations react with the phosphate anions present in the stream to form an insoluble iron phosphate complex. This iron phosphate complex is removed from the process via the precipitated and dewatered biosolids. Through the process of phosphate binding with iron, phosphorus levels in the plant effluent can be reduced significantly. This reduction in phosphorus also reduces the phosphorus loads returned to the plant headworks. Phosphorus can be removed with 90+% efficiency, and the final phosphorus concentration is lower than 0.5 milligrams per liter and as low as less than 0.1 milligrams per liter. The addition of iron-based chemistry for P removal will also positively impact BOD and suspended solids removal rates. Biological systems can be supplemented with an iron coagulant to achieve ultra-low phosphorus levels. Chemical P removal is a reliable backup to biological P removal since it is less subject to water chemistry and process flow upsets compared to biological systems. Chemical treatment systems can be used to ensure P removal is compliant by precipitating any residual phosphorus left after biological treatment. The first step in chemical phosphorus removal is to determine the coagulant dose required to obtain the desired phosphorus concentration in the plant effluent. Determining the coagulant dosage begins by establishing the soluble phosphate level in the wastewater to be removed. Phosphorus in wastewater is separated into three main fractions: inorganic orthophosphate, inorganic polyphosphate, and organically bound phosphorus. Chemical pee removal is based on two different mechanisms, chemical precipitation and physical removal, known as sweep coagulation. Chemical precipitation of phosphorus converts dissolved or inorganic phosphorus compounds, mainly phosphates, to a low solubility iron phosphate complex. Metal hydroxide forms and creates a gelatinous flock that aids in binding the iron phosphates and the suspended solids, including organically bound particulate phosphorus. The wastewater contaminants become entangled in the hydroxides, causing most remaining contaminants to be swept down with the settling hydroxides. This process is known as sweep coagulation. The ratios of coagulant to soluble phosphorus and phosphate for Fe+3 iron are 1.80 for phosphorus and 0.59 for phosphate. When dosing iron, the presence of soluble phosphate indicates an insufficient coagulant dosage. The presence of insoluble phosphorus, also known as organically bound particulate phosphorus, in the wastewater can be caused by poor settling conditions. This issue can be addressed through adjusting hydraulic loading rates, mixing adjustments, introduction of polymer dosing, or providing additional flow capacity. Phosphorus can be removed with up to 90+% efficiency, causing the final phosphorus concentration to be lower than 0.5 milligrams per liter and as low as 0.1 milligrams per liter. Now I'm handing it over to Ricardo, who will tell you more about coagulant addition points and dosing.
Thank you, Richard. Iron coagulants can be added in the primary, secondary, and tertiary areas of the wastewater treatment plant. Single point or multi-point dosing can be utilized to reach the desired phosphorus level. A primary coagulant can be used for a single or multi-point dosing, or a secondary coagulant can be used in combination to reach ultra-low phosphorus level. An example of this will be to use a ferrous coagulant in the aeration tank and a ferric coagulant in the secondary clarifier as a polishing treatment. This combination will help to achieve ultra-low phosphate limits below 0.5 milligram liter. Iron addition not only results in reduced phosphorus level, but also has many downstream benefits. Iron coagulants can control odor and corrosion. Dissolved sulfides can be removed via iron sulfide complex precipitation to prevent hydrogen sulfide gas. The removal of phosphate ions in wastewater treatment results in both the treatment and prevention of struvite in plant process. Struvite forms in facility with anaerobic digestion when the levels of soluble ammonia, phosphate, and magnesium are elevated due to the breaking down of active sludge. By precipitation of the phosphate precursor to struvite, iron coagulants effectively stop struvite formation. The reduction and prevention of struvite improves sludge pumps efficiency and reduce operational maintenance and cleaning costs. Adding iron improves cake dryness, enhancing biosolid dewatering, and lowering the hauling cost. Reducing the dewatering polymer demands also lower chemical treatment costs. Some inorganic coagulants contain up to 80% or more recycled content. Chemera is committed to carbon neutral by 2045 and reduction of 30% by 2030. And now I'm handing this over to Richard, who is going to present a case study.
Water reclamation facility highlighted in our case study treats an average daily flow of 17 million gallons a day with a 25 mgd capacity and utilizes submerged membrane bioreactor technology to produce reclaimed quality effluent. The issue facing the customer: discharge permit requirements allow only 35 pounds of phosphorus per day, or approximately 0.23 parts per million during March through October. The plant needed a solution for reducing phosphorus levels during these months. The solution offered by Chemera. Studies conducted at the North Las Vegas facility showed an increase in phosphorus levels when water temperatures reached 82 degrees Fahrenheit. Chemera introduced ferric chloride to chemically remove phosphorus compounds by adding 200 to 400 gallons per day of ferric from March through October. The result: improved water quality, phosphorus discharge limit compliance, improved biosolids production, and biosolids process cost savings. Handing it back to you, Ricardo.
Thanks, Richard. The sustainability of phosphorus removal through chemical treatment can be enhanced using digital automation. Optimization of coagulant dosage can be tightly controlled through this emerging technology. Ultra-low phosphorus limits require high ratios of iron coagulant. Therefore, precise continuous monitoring and dose control is essential to managing cost and resources consumption. This becomes especially important when facing water flows and quality variation due to storm events and industrial contribution. Kemira offered an intelligent chemical management platform called ChemConnect-P. This smart technology does and optimize the amount of coagulants for chemical peel removal. It uses continuous monitoring and precise dosing control to react quickly to fluctuating wastewater conditions. And I'm handing this over to Chris, who will give you the conclusion of the benefit of iron coagulant for phosphorus removal.
We might have lost Chris there in a connection, but I can sum it up here quickly.
Sorry.
There you go.
I was on mute still. Sorry. Thank you, Ingrid and Ricardo and Richard. In conclusion, the benefits of iron coagulants for phosphorus removal are improved water quality and compliance. Iron coagulant addition works to settle out not only the metal phosphate compounds just formed, but also any other suspended solids in the waste stream. This enables reliable compliance with stringent phosphorus limits and NPDES permits. Also, there are sustainable downstream benefits and cost savings. Some additional benefits of using ferric salts are that they remove hydrogen sulfide, enhance cake dryness, and treat struvite in the entire process. Optimized coagulant usage results in less chemical sludge and therefore lower biosolid disposal costs and reduced polymer usage costs. This is due to the downstream benefit of higher sludge dissolved solids obtained through the addition of iron coagulants. Thank you everyone for your attention.
All right, this was great. Can everyone hear me okay?
Yes, we can.
All right, perfect. So we will go ahead and dive into Q&A. And if you have not already, go ahead and change your to option to everyone to make sure that I can see all of your questions that's coming in through chat. And I will go ahead and go with our first question, which is, can you discuss the benefits of adding iron at multiple points in the treatment train for TP removal and benefits in reducing TP dosage compared to feeding at a single point? There was a mouthful, but it is there in chat. And if one of you would love to go ahead and respond to that question.
Regina, I can handle that. The benefits of multiple point injection are that we call it the second addition point of trim feed, and often the primary feed point handles the bulk of the loading, with the trim feed providing a secondary amount. So in other words, with a single injection point, if for some reason the load to the plant increased and there weren't sensors in place to automatically adjust the feed, and the initial feed did not provide sufficient levels of TP removal, The secondary application point would provide the buffer, would provide the additional TP removal requirement.
All right, perfect. Again, we've got several minutes remaining. If you would like to ask a question or just make a comment in reference to today's presentation, go ahead and change your to option to everyone so that we can see your question or comment. And panel, if you would like to make a closing statement or just a comment to summarize anything that we've talked about, now is a great time to do that. And so we do have another question coming in. Can you share any data on re-release of bound phosphorus based on pH in under aerobic, anoxic, and anaerobic conditions, equilibrium constants for different pH, and DO or graphs?
We can certainly provide that information in a follow-up communication. If I can get your contact information, I definitely can be happy to provide you with additional information via an email. That's an awful lot to ask for, but we can put something together.
Yeah, sure. And you will be able to, the panel will receive the chat as well as the attendees' information. So you will be able to reach out to them afterwards as well. And so how often do operators attempt biological foes removal combined with chemical reduction of P? I don't know if I can see the whole thing. And what are the benefits versus cost?
I'm sorry, Regina, I wasn't clear on that question. The question is the benefits of chemical P removal versus biological?
Yes. Let me see. How often do operators attempt biological foes removal combined with chemical reduction of maybe P? He just has a P and a question mark. And what are the benefits versus cost?
Okay, I think I understand what you're getting at. I can answer that. Most of the plants that we deal with, they adjust their chemistry addition manually. That's based on measuring the phosphorus load several times a day or once a day. One thing I can add is Chimera has a platform where the chemical dosing to achieve a target rate of TP removal is automatic. It works on a 24/7 basis.
Okay, and I believe you probably responded well to his question because he did repost it and just kind of cleared it up. The P was supposed to be for phosphorus.
Ricardo?
If I can add, if I can add to Richard respond here, we often have a chemical application on biological process when you have a time limit and you are not able to treat it biological, you can add a chemical addition to help you with your permit to the P removal rate. So we often do that.
All right, perfect. Thank you, Ricardo. We've got another question that has come in. Can you provide any comments on impacts of iron-based P removal versus aluminum-based P removal and impacts on downstream UV disinfection systems?
Certainly, I can handle that. Obviously, those plants that have UV disinfection have to be careful of an iron overdose. I can tell you that if iron is applied correctly, there should be no issues on UV disinfection. As far as the difference between chemical P removal using iron versus chemical P removal versus aluminum, one of the biggest impacts we see is on dewatering. The aluminum hydroxide it contains a lot of water within its structure and is more difficult to dewater than iron. And in fact, iron is known to enhance dewatering, as we have many applications where we use iron in the dewatering process to enhance dewatering. Ricardo, do you want to add anything further?
I agree with you. I mean, the benefit is going to be the downstream benefit that adding an iron salt will have versus aluminum salts.
Okay, thank you. And we've got another question that has come in. Can you provide any comments on impacts of iron-based I think I just read that one. Iron-based pee removal versus aluminum-based pee removal and impacts on downstream UV disinfection systems. I believe you all just responded to that one.
That was the question.
If you use iron-based pee removal to primaries, will it settle out with the primary solids?
Yes, it will. If we have many customers that utilize an iron-based chemistry fed into the inlet to the primary clarifier / headworks, and absolutely the resulting flock formed will precipitate out in the primary clarifiers.
And do you have a preferred online phosphorus analyzer when providing automated controls?
Ricardo,
yes, we don't. We visit your plant and we adapt our technology to what you have in the plant available. If you have already some instrumentation, we can use that. If not, we use what can fit in the plant. It is barriers depend on the plant. But I can say, both we use on the phosphate analyzer is going to be hack or it's going to be a stem scan. So those are the two analyzer modes we use, but we adapt to your plant.
All right, perfect. Again, we've got several minutes left. If you all would like to post a question, just go ahead and change that to option to everyone and let us know of your question.
I would like to add, Regina, that if any of the participants are interested in learning a little bit more about our P Optimizer platform that automates the ferric dosing for optimized phosphorus removal, if you want to reach out to us, we're more than happy to provide you with technical literature, case studies, et cetera.
Perfect. Thank you. All right. Can you discuss co-precipitation of other metals when iron is used for pee removal?
I'm not quite sure. Forgive me. I'm not quite sure. I understand the question, unless you're talking about using another metal in conjunction with iron for pee removal. Can you elaborate on the question, please?
Yeah, Steve, if you want to elaborate on that question, just go ahead and elaborate a little bit more in the chat. Okay, he goes on to elaborate by stating, I have a client, oh, that's Jim Fisher, I'm sorry. So Steve, we're going to go to Jim while you're elaborating. I have a client with a 0.06 milligram per liter limit. Do you believe an online analyzer can be used for this low of a limit, given only a portion of the residual will be orthophosphate that an analyzer can measure?
Ricardo?
I believe it can be done. The recommendation is to visit the plant, do the lab work, and do a couple trials to obtain more information. But yes, I believe it could be done, even if it's that low.
Okay, perfect. And Stephen has not elaborated yet, but I will also just reiterate that the panel will receive these questions and your contact information. And so if they would like to elaborate with you, they will. And he also goes on to say, iron commonly helps in removal of other metals like copper, zinc, etc., due to sorption in the flock.
That is correct.
All right. And Steve, did that clear that up for you?
Obviously, if that is a goal of the client plant, when conducting laboratory tests, metals analysis on the target metals would be conducted on the settled treated samples to verify the rates of removal of the co-precipitation of the other metals.
Okay. I don't see any additional questions coming through. If the panel would like to summarize anything or make any closing statements, now would probably be a good time to do that. We do have one from Jim. What does ferric chloride cost in the Midwest at this time?
Well, it depends on the end location. If you wanted, I could send you more particular information. But I'd like to finish by adding, Ricardo and I travel around the country performing detailed site surveys. For those participants who are not doing anything at present but anticipate requiring to enhance phosphorus removal, we're more than happy to set up a site visit to conduct a detailed survey of your plant, conduct laboratory tests, recommend optimal coagulant injection point or points. That's part of the service we offer, and we're more than happy to offer that to the participants.
All right. I believe Steve is saying it would be nice to have some technical papers, et cetera, on this benefit to help support us in discussion with regulators, clients, et cetera, when choosing a P precipitation chemical.
Absolutely. Ricardo and I have a pretty deep library. For those of you who don't know, Chimera is a European company, and between case studies generated over here as well as in Europe, we've got a pretty deep library of providing an overview of the applications and the benefits.
Okay. I am just checking the chat, just making sure that I was able to cover all of your questions. Still have just a few more minutes. If anyone wants to post a last minute question, please go ahead. And if not, I'm going to go ahead and ask our panel to go ahead and say just a few last closing statements, and then we'll go ahead and close out for today.
This is Chris Hill. I want to thank everyone for joining us today. And if you have follow-up questions, please contact myself or one of my colleagues to get more detailed technical information, as have been requested in the chat box today.
This is Richard Watrous. I'd just like to comment that I know a lot of you, be it plant operators or engineers who have clients that are facing tightened phosphorus discharge limits and are questioning what options you have out there. Chimera can offer you a myriad of options, and rest assured that we're able to help you achieve your tighter phosphorus discharge limits that are being imposed on you by regulators.
This is Ricardo here. Thank you for joining this webinar. Any questions or anything you need, as Richard mentioned, we are able to visit your plants and provide the information needed. So don't hesitate to contact us. We are here at your service. Thank you.
Thank you.
All right, perfect. This was great. Thank you so much to our panel. Thank you to our sponsor, Chimera. This will conclude today's e-showcase, and thank you attendees for attending today's event. The recording will be available at wetfiresguide.wef.org, and we will send all registrants an email tomorrow with that link. And please visit our event calendar to sign up for future webcasts. Thank you, everyone.
Thank you.